In general, static systems can be subjected to multiple loads. And so we could have some static system and lots of different things could be happening to it. We could have a bunch of different forces all doing different things. And one of the things that Newton's laws tell us is that the sum of these forces is important. And so what we're going to talk about here is how to add force vectors together. And when we do that, when we add vectors, the thing we end up with is called the resultant. So when we add a bunch of forces together, we get what would be called a resultant force vector. I'm going to show you 3 ways to add vectors together in this video. The first is graphically. The second is using geometry or trigonometry. And the third way is using the vector components. And depending on what information you have available, each of these methods is going to be useful or most convenient anyhow in different circumstances. So let's start by adding graphically. Literally, what I'm talking about here is that we have some sort of a grid. And just to keep things simple, I'm just going to draw a three lines here and 3 lines like this. If we happen to have vectors that fall nicely on a grid, it's quite simple to add them together using this. So for example, maybe we have one vector that goes up like this, and another vector that goes up like this. To add them graphically, all we do is position them head to tail. So for example, this one goes over to an up 1. I'll take it here and go over to an up 1 instead, like so. And the resultant now is this vector here. And we can literally count the boxes and see that the resultant here is 1, 2, 3, 4 in the x direction and 1, 2, 3, 4 in the y direction. One of the things you should know is that it doesn't matter which order you do this in. So real quickly here, let me try and replicate this. 1, 2, 3. Of course, these things aren't even close to being to scale, but that's okay. Same 2 vectors. Let's see if I can even. So we go up 2 and 2 on that one, and the other one was up 1 and over 2, like so. If we were to add them the other order, so we move the pink one here, which goes over 2 and up 2, like so, you'll see that we end up with the exact same resultant. So it doesn't matter which order you do this in, we're just going to position them head to tail and then add them together. The next option is to adding using geometry or trig. And a couple options here. So start out with these 2 vectors that we want to add together, one like this and one like this. And again, we can either think about positioning them head to tail, or we can think about this using what's commonly called to as a parallelogram rule, which is, well, that was poorly drawn. Let's try this again. I want to draw parallel lines to the vectors, and the resultant here is going to split the difference like so. And depending on what information you have, you can either solve this as a parallelogram or as a triangle. You see here that it forms 2 triangles or a parallelogram. Some handy geometry facts that you might put to use here is that for a triangle, the sum of the internal angles is equal to 180 degrees. For a parallelogram, the sum of internal angles is 360 degrees. And then also, if we wanted to label a triangle using this notation here, let's get this out real quick. We could call this side A, B, and C, and then the opposites from each of those angles. So A is opposite alpha angle, B is opposite beta, and C is opposite gamma, first three Greek letters. The law of sines and cosines come in handy. Law of sines tells us that A over the sine of alpha has to be equal to B over the sine of beta, which has to be equal to C over the sine of gamma. And the law of cosines then tells us that C is equal to the square root of A squared plus B squared minus 2AB cosine gamma. And so these two relations, depending on what we know in terms of how long the vectors are or the angle between them, things like that, we can actually use this to solve the triangle and write out all the sides and all the angles and then add things together that way to find, say, this unknown resultant vector and how big it is. The last way to add together is using the vector components. And so the way this would work, again, if we have our two vectors that we've been looking at here, exaggerating a little bit here, I'm going to call this one F2, and we'll call this one here, say, F1. They have components, right? And so we could project, if we call this the X and Y axis like so, we could call this here F1X and this side here F1Y, and do that again here. We have F2X, F2Y, and you can see I already positioned them head to tail, but what I want you to realize is that the horizontal component of this resultant vector is just F1X plus F2X, and the vertical component is F1Y plus F2Y. So if we could write F1 as F1X times I hat plus F1Y times J hat, and we could write F2 as F2X I hat plus F2Y J hat, then we could write the resultant F1 plus F2 as F1X plus F2X times I hat plus F1Y plus F2Y J hat. Some people like to use the bracket notation. That's cool too. So you could write this as F1X plus F2X comma F1Y plus F2Y, and use little hard brackets here. I prefer the I's and J's, but both notations work. So here's the thing. We can add up the applied forces acting on any system just by doing this over and over again. So if we had a more complicated system with lots of forces applied to it, say something that looked like this, some F1, F2, F3, F4, F5, and these are all vectors, then we could do this in pairs. Add F1 and F2 together, then the result of that, add F3, F4, F5, and so on, and you could do that using any of these three methods. This might feel a little weird on rigid bodies because the forces are spread out and you know intuitively there's more going on here, so it should feel a little weird. The moments caused by each of the individual forces have to be accounted for too, and we'll do that by finding the moment caused by each individual force and then finding a resultant moment, but that is the topic for another discussion. For now, what you need to know is we can add up all of the applied forces on a system and replace them with a single resultant applied force that has the exact same effect.